So I'd like to acknowledge our wonderful branch partners and sponsors for this year. Firstly, BV, or Bureau Veritas, has been with us for many years, and it's great to have them on board as one of our branch partners once again. And Oz Minerals, who are our other branch partner this year. Great to have them on board as well. Thermo Fisher are our sponsors of the Technical Lunch series. So again, and have been with us for quite a few years now, and welcome to the guys from Thermo here today. And finally, Heatgate, who are our media partner. So you'll see their logo on the bottom of all our media posts that go out. So it's really thanks to those sponsors that we can offer these lunches today at the subsidised prices that we do for members, and also to continue the loyalty card scheme that we've got going. So for members who came in today, hopefully you got your stamp on your loyalty card, and just like when you go to the coffee shop, when you come here for the 6th technical lunch towards the end of the year, it'll be a freebie. So thanks again to our sponsors, we're able to provide that. We have one last reminder about the photo competition. So we've been talking about this for a little while, but I'm sure you're all snapping photos on your phone all the time. So I encourage you to have a look through any of your photos that you've taken of work-related photos for the year and get them sent in. We've extended the deadline till the end of April. So it'd be great to get a few more entries, and you can see last year's winner there of some beautiful bubbles taken by Mark Wiedenbach. Alright, and again just a final reminder on the name badges like these ones that you see some of us wearing today. We've decided to give our regular attendees free name badges that they can wear along to these type of events. Some of you probably got personal invitations recently asking if you would like one, but if you didn't and you would, please reach out to Chris or I today and we'll put your name on the list. Again, closing that off at the end of the month, so we'll get them into production. Alright, so to talk about a few upcoming events that you can watch out for and look forward to, our May Technical Lunch will be right here on the 20th of May. Featuring James Marsh from Andromeda Metals. He'll be giving us an update on his company's industrial minerals projects, including the world-class halloysite kaolin deposit right here in South Australia. So a good project-based talk. And if you're wondering, I did practice saying halloysite. Hopefully I got it right. So look out, we'll get some emails out about that one really, really soon. Then in June, we have Nigel Cook from University of Adelaide, speaking about the research work in the copper and uranium hub, which also should be really interesting, and welcome Nigel along today. Really exciting one for you to all put in your calendars. In July is our really popular annual dinner, which again will be in this room right here on the 16th of July. I'm pleased to announce today for the first time that our guest speaker will be Associate Professor Alice Gorman from Flinders University. And if you don't know Alice, she's an internationally recognised leader in the field of space archaeology. Her research on space exploration has been featured in National Geographic, New Scientist and Archaeology magazines. She's worked extensively in Indigenous heritage management, providing advice for mining and other industries. She tweets as Dr. Space Junk, and you can often hear her talking about space on ABC Radio. So it should be a great evening full of awards presentations, prizes, catching up with friends, and a great talk by Alice. So again, we'll get the registrations out for that one really soon, but put that one in your diaries. All right, before we move on to the presentations, we have our usual door prize draw. So I'll ask Chris, because he's Chris Chester, because he's closest to me. Thank you very much. We have an orange ticket C76. And we have a winner over there with Marie, so well done. So the winner of Marie gets a $50 voucher for the Ausim store that she can spend on a publication or on tickets to events like this, so well done. Alright, so move on to the presentations now. For the past few years, the Adelaide branch has worked closely with the local student recipients of the Ausim's EEF, Education Endowment Fund, and also the Adelaide branch's own joint scholarship with the Playford Trust, by giving guidance and mentors, plus the opportunity for those students to network and present a short talk at one of the events like this. So today we're pleased to have one of these talks from Michael Shaw. Michael's currently studying mining engineering at the University of Adelaide and set to complete his degree in mid-2022. He's completed vacation programs at Carrapateena and Prominent Hill, and he's enthusiastic for further exposure to the mining and minerals industry. So please welcome Michael. There you go.
Thank you all for attending the Adelaide luncheon meet today. It's a pleasure to have you all here and hope you feel welcome. My name's Michael and I'm a fourth year mining student. I'd like to tell you a little bit about my honours project, hybrid analysis of ore pass design. Firstly, I'd like to make some acknowledgements to my team and my supervisors. Thanks to Barton Risky, Blair, Palmer and Jason O for being a great team, as well as Marat and Chris for providing guidance and additional knowledge to our project. So most of you might know what an ore pass is, but however, it's a vertical shaft which is used to transport rock mass material from descending levels. This method is used to save money on transportation costs and also increase production rates within the mining operation. However, there are some problems which are encountered with using ore passes, and these are encountered with hang-ups, which are blockages within the actual ore pass itself, causing a halt to production. And there's also unpredictable life expectancies encountered with using ore passes due to the overwearing in the early stage of the ore pass, which causes premature closure, and the capital costs will not be justified. So to analyse these methods, we'll be using numerical models, as these help us solve the difficult problems. However, with the rocks, as we know, they're very irregular and they're not continuous like most structures in terms of the mineralogy and stresses within. So to do this, we can define it as continuous or discontinuous methods. And so as you can see, on this side we have a continuous as well as the other side. And here we will assume that the rock is a soil-like mechanics or it's actually a solid structure and the forces will be dispersed evenly throughout the material. On the other hand, we have discontinuous methods in the centre here, which will assume the rock's more a block-like structure with joints and fractures throughout the material. And here the force is actually dispersed adjacently to perpendicular on the materials, and it has more of like a domino effect throughout the model. So using the continuous and discontinuous methods, we can assign a discrete element method to the actual ore pass material that's flowing through the ore pass. This is done using a particle flow code, also known as PFC 3D. And they use these synthetically made rock clumps which are on the side here, which is made by connecting 100 of small spherical balls. And then using 100 of these clumps, we can actually simulate the ore pass flow through we can actually simulate the material flow through the ore pass. And here we actually have some cohesive arching, which is a type of hang-up that's actually occurring in the ore pass. On the other hand, for a continuous, we're going to use continuous rock for the finite difference method, which uses the Fast-Lagrange analysis of continua program, or just a bit of a mouthful, but easier, it's just flat 3D. And then, how that works is we'll use a mesh, which is applied to the surface of the ore pass, and then the deformation in that mesh will actually allow us to make that geotechnical analysis. So you might be wondering what's the hybrid model come into it. So this is actually combining both the continuous and discontinuous methods, FLAC and PFC 3D. So by combining those codes, we can analyse the flow of the material and then use the forces created within that to apply that onto the actual ore pass itself. So here we've got two examples of the basic hybrid model. One we're using the flow of clumps and the second one we're using the flow of balls. In comparison, these two, we can actually see that the flow of clumps has a higher impact, is impacting higher on the ore pass compared to the flow of bulks. So our clumps has a more direct impact on the wall rather than the flow of the bulks. So we aim to make a more sophisticated model using this hybrid model and actually make it more of a representation of a period over a time rather than a single cycle like before. This will help us identify the critical points within the ore pass and allow us to determine whether we need further reinforcement or lining within the structures. This will allow us to evaluate the initial mine design and create a stable and reduce the risks of further hang-up within the actual ore pass. We're working with Oz Minerals and using their designs and data from their project at Carrapateena to build our model to help assist them with the management and usage procedures for further use and as well as in further industry. Thank you.
All right, thank you very much, Michael. We'll have some question time for both Michael and Chris at the end, so save up your questions for Michael till the very end. So on to our main presentation now by Dr. Chris Chester. Chris commenced his career in 2001 with rock mechanics technology in the UK, primarily focused on the development of novel remote instrumentation for use in the coal mining industry. Since moving to Australia in 2005, he has worked at various operations covering gold, nickel, copper and zinc commodities, currently working at Oz Minerals on the Carrapateena expansion project with a focus on building strong foundations of Orebody knowledge to minimise risk and maximise value. His talk today is on caving rock mechanics and the Carrapateena block cave design. So please welcome Chris.
Thank you very much, everybody. Thanks for the introduction, Stu, and to Michael. You've lifted the bar there for the presentation, so hopefully we can maintain that high level. So as introduced, my name is Chris Chester. I work for Oz Minerals. I'm leading the Orebody knowledge team. We're looking at the expansion of the Carrapateena project, where we're looking at transitioning the SLC to a block caving application. So my talk today is really around caving rock mechanics and the design process that we're going through at the Carrapateena Orebody. Now, caving rock mechanics is a very broad subject matter, so I've broken it down into essentially covering 3 specific hazards associated with caving and Orebody knowledge, just so that we don't dilute the presentation too much, and I can give you a little bit of detail. So without further ado, obviously the obligatory disclaimers, so I'll ask questions on this later for those who've read it. A little brief introduction in terms of the content. I'd like to speak a little bit about a gentleman called Dennis Laubscher. People who are involved in caving will have heard this gentleman. And then I'm just going to go a little bit more detail about myself, just to personalise the presentation, more to give the younger generation in the audience a bit of an understanding of how I got into rock mechanics. Perhaps they're interested in following that route. I've mentioned that I'm leading the Orebody knowledge team, so I'd like to talk a little bit about what Orebody knowledge is and where we see the value that is. And then we'll start discussing around the actual caving hazards and the mitigation controls that we're putting in place to mitigate those risks and hazards. And then we'll get to the question and answer session at the very end. So firstly, I'd just like to recognise a gentleman called Dennis Laubscher, who's considered really a titan within the block caving community. Sadly, he passed away earlier this year. I've just noted a few of his achievements over the years, really dating back all the way to the 1970s, where he introduced the mining rock mass rating, rock mass classification system, often referred to as the Mr. or MRMR. He's also authored a number of textbooks which are used throughout the caving community in terms of design and knowledge around caving. And then as part of the SRK consultancy group, he's consulted a number of different caving operations, so a huge wealth of knowledge that he built. And that was recognised by the South African Institute of Mining Metallurgy when they awarded him the Brigadier Stokes Medal, which is the image on the right there. I'll actually be talking about some of his design work. We actually apply some of his work in our design process, so it's relevant really that we recognise the sad loss of this gentleman. So a little bit about myself. You don't often get a chance to talk about yourself, so why not just really about how I became part of caving community. So originally from the northeast of England. My accent doesn't give it away. I've sort of lost it over the years, but I was born in the northeast of England. It's actually an iron ore mining community. It's marine ironstone, so quite low grade, 30% sort of grades. But it's what built the community up. So as was the case in the sort of the early 19th century, the mine supplied everything. So the church, the hospital, the terraced housing, all as a result of the mining history there. In fact, I actually had a cut on the base of my chin, which was a result of the mining, but it's probably more a result of my cycling ambitions being greater than my cycling skill. So I tried to descend one of the old waste heaps that's left behind in the community and didn't quite make the bottom on the bike. So yes, I guess just there's mining in my blood to some extent. There is somewhat of a link with ironstone mining. Cleveland Bridge Company is a local manufacturing. They actually designed the Sydney Harbour Bridge, and the iron ore was mined from the hills of the Cleveland Hills. So there's a bit of a tenuous link with Australia. Anyway, I attended Camborne School of Mines, where I did some research, as Stuart alluded to. I did some research in remote sensing rock mechanics, mainly around what used to be British coal. From that point, finishing that research, I moved on to Australia to work in a number of different mining operations. So for the 16 years I've been here, about 50% of that time I've been working in sublevel caving and block caving, which is a fascinating and challenging and an interesting area of the mining industry, which I can only see getting larger as ore bodies become the grades drop, and we're looking at economies of scale. So now I'd just like to talk a little bit about ore body knowledge and where we see value from ore body knowledge. So it's a little bit of a catch-all term. I've spoken to one of the gentlemen here already that it covers all of the sort of earth science areas. So within Oz Minerals, especially with the expansion team, we see geology, geotechnical engineering, structural geology, hydrology, geometallurgy, all come under the banner of ore body knowledge. Historically in the industry we tend to treat these disciplines as separate silos that don't readily talk to each other, and when they do it's almost forced. We're looking to build this understanding where there's an interdependencies and interrelationships between these disciplines and forcing them to talk much more readily to gain that benefit of that ore body knowledge. So that's essentially a little bit of the background. But why do we see benefit in having ore body knowledge? Well, it doesn't take long to search around the industry or the history of caving to find a few headlines. So the first one here is Rio Tinto's reported cost blowout for their Oyu Tolgoi operation, roughly $2.7 billion reported in the last couple of years in terms of cost blowout. Essentially, that comes down to having late-stage ore body knowledge coming into the design process, where they've had to have a rapid redesign of their cave as a result of understanding their structural setting much too late in the piece. Second example from the Newcrest, so the people may be aware of a significant earthquake or seismic event that the Cave East mine suffered a couple of years ago. That impacted their production quite significantly. Their production was down for several months. Again, could be attributed to ore body knowledge. And finally, a much more sad situation. So this is a heading taken from the North Pax disaster, for those people who are aware. North Pax was owned by Rio Tinto at the time. They were in production. The cave stalled during its propagation to surface. Unfortunately, production continued and they generated a large air gap in the cave column. At some point, that cave back released, resulting in a pressurization of the void space in the air within it, which escaped along one of the tunnels, resulting in the sad loss of 4 lives. Again, could be attributed to the knowledge of the ore body and the actual implementation of that knowledge either through the strategic design phase or through the tactical management phase of the cave. So hopefully you can see that there's real value and benefit, not only from a safety perspective, but from a production perspective, to have good ore body knowledge. And that's not just geology, geotech, that covers the whole suite of those earth sciences. So we spoke about hazards associated with caving. So there's a number of documented hazards or hazards related to caving and ore body knowledge. So I'm briefly going to highlight them all, but I'm going to talk in a little bit more detail about 3 of them. So the first one I've sort of lumped together, which is caveability and cave propagation and cave flow. So this is all about recovering the resource safely, whether it's broken material or unbroken material. The next one relates to mine-induced seismicity. This is earthquakes that we're generating underground as we redistribute stresses due to the void volumes that we're creating. Next on the list would be excavation stability. So we're dealing with variable material properties and high stresses, and these material properties act differently when loaded. So you've got a very deep caving operation, high stresses and soft ground. The likelihood that you see instability is quite high. Material inundation, so like air being forced into the workings, you can also have mud. So the mixture of fine materials and water can actually inundate your workings. And the final one to recognise is material dilution. This is where your low-grade, maybe overlying material enters your ore stream at a much earlier stage than when you forecast, therefore reducing obviously the economics of the mine. So that's a little bit of a rapid fire sort of highlight of the caving hazards as we've documented. In terms of the mitigation controls, we use the hierarchy of control to categorise those different controls which are in place to manage these hazards. So hopefully most people are aware of the hierarchy of control. It's essentially categorised into 5 different bands ranked by its effectiveness. So at the very bottom you have PPE or personal protective equipment. That's the least effective at controlling your hazards, all the way up to elimination, which is your most effective. Essentially, you're removing that hazard. It no longer exists. It's therefore benign. For the sake of this presentation and for some of the terminology we use, I've categorised them again into 2 separate bands. One is tactical. Now, tactical controls look at the lower order hierarchy of controls, which are your PPE, your administrative controls, and your engineering controls. And these are the controls that you're most likely to implement during the operational phase or the construction phase. Designs are already put in place. It's very difficult to change those designs. Therefore, you're left with putting in tactical controls. From my perspective and from a design perspective, strategic controls is their bread and butter. This is where we focus our efforts, is making sure that we're implementing correct strategic controls to manage these hazards. So they're the eliminations, they're the substitutions, they're the engineering controls. Much better to put in the design phase at the very beginning. Very, very hard to adopt these during the actual construction or operational phase. So for this presentation, I'm really just focusing on these strategic controls because this is the area that we're working in at the moment with the design. If I was to go through all the tactical controls, we could be here for some time because these are significant hazards. You need a multi-tiered hazard control. So let's dive into the actual hazards themselves. So the first one we're going to talk about is the caveability and cave propagation and cave flow. So I've lumped these 3 together. You could separate them if you wanted, but for the sake of the presentation, I've kept them all in one. So we've got a bit of an image to try and help explain, but caveability essentially is the successful caving of the cave propagation across the entire economic resource, all the way to surface or to an overlying void space. So for the sake of Carrapateena, we will have a sub-level cave void volume above our block cave. So we're looking for the safe propagation to connect with that void space above. Other operations like the caviers will propagate all the way to surface. And it sounds a very simple, straightforward process. We've all been into natural caves in our lives. We don't question about going into these natural caves. Imagine those caves making their way all the way to surface. That's essentially what we're trying to do. So what is the consequence in the event that we don't achieve desired outcomes of cave propagation? Well, We've already spoken about one, so the cave store situation was what was happened at the North Parks situation with their air blast. The cave back has reached a stable position, production has continued, generated an air gap, and potentially can lead to an air blast. That's an extreme scenario. Hopefully with the understanding of that risks now that we will never get to those sort of consequences again. A more likely scenario is a reduction in your production rates, your ramp-ups, your availability of tons, mainly because you have to re-divert while you're doing your production to manage the cave stall event. In terms of the resource recovery, this is referring to the event where the cave has propagated to surface or through to an overlying void space. However, it hasn't widened to the width that you're expecting. It's essentially left resources and reserves in the flanks of the cave. The opposite impact there is a reduction in ore stocks. Impact is on your mine life as well, and it can actually lead to mine dilution coming in much earlier because you don't have as much grade material to draw. You can actually pull in diluted material. So on the images here, the darker images of North Parks, you can see this very steep shape here is essentially a chimney type cave. They potentially can be leaving reserves in the flanks of this cave unless they're able to manage the growth of that cave further. And on the right hand side is just a simple schematic of the air blast scenario. So just a very brief overview of those hazards. Now I'd like to talk about the actual design processes and the controls that we put in place during the design process to eliminate those hazards. So firstly we look at the empirical design charts. So we spoke about Dennis Loucher, this is part of his early works. He essentially looked at a number of benchmarking operations and plotted them on an empirical chart, which is plotted against his mining rock mass rating, his MR&R rock mass classification scale, and a geometrical variable called hydraulic radius, which is simply area over perimeter of the cave back. So it's very simple but quite a powerful tool from an early stage design perspective. You can plot your design upon this graph and see how you compare against other operations in terms of capability. There's a transition zone and then there's a stable zone. So if you plot in this area, you're obviously potentially a stable cave. This is a transition zone with these two defined by these two lines, and then this is in the caving zone. So ideally you want to be plotting in this caving zone here. Otherwise you look to adjust your designs. There was other capability charts and stability charts by the likes of Orebody and Morsley, but they're focused mainly on stoping. So this is specific around cave propagation. The next area we look at in terms of strategic control is moving into the numerical modelling, and we've already had a bit of a discussion about numerical modelling and the use of the FLAC. So we're using a numerical cave simulations using a bidirectional coupled model. So when I say bidirectional, it's two different codes linked together and they handshake backwards and forwards. So you use continuum refinement difference codes, so the FLAC 3D codes, to model the progressive failure as the stresses and strains cause the rock mass to fail and disintegrate into finer material. Then we use a cellular automata code referred to as cave sim, and that simulates the gravity flow. And between the two models, they handshake backwards and forwards, and that develops the most effective simulation of the caving condition, which is extremely complex. It's still really beyond numerical modelling to get it extremely precise, but this is the best we have. With the development of modern computer technology and computer speeds, we can actually now run some multivariate analysis where you, at the early stages of a mine design, you're limited in your ore body knowledge. So because of the uncertainties you're faced with, you run a full sequence of models with a whole range of variable inputs, and then you can look at obviously the outputs of those. As you grow more knowledge, you get more performance data from your mine, you can then start looking at validation and calibration of your models, which gives you more confidence. You're reducing those uncertainties in your model forecasts. In terms of forecasts, we can determine cave rates, the propagation rates. We can determine the resource recovery, so how much of those cave flanks we expect to actually consume. We can see the stresses and strains built up around the actual model, so that the hotter the colours are the higher principal stresses. We can look at flows within the cave, and we can also look at the likes of subsidence on surfaces and subsidence on the ground as well, which all helps you then improve your mine design. You're moving your infrastructure further away from high stress areas and so on and so forth. So the next control is around cave engineering. Cave engineering, there's the two options which you can use individually, or you can use together as a hybrid engineering control. The first is blast preconditioning. Essentially you're drilling long hole blast holes, charging them and firing them. The actual spacing between your blast holes is quite large. You're not looking to rubberize that word, I'll even try it again. You're not trying to fragment the rock too much, you're only looking to crack the rock. It's not a development round, it's just to put some extra fractures in there. The other option is to look at hydraulic fracturing, which is the use of high pressure water injected into wells, essentially installing additional man-made fractures, horizontal fractures in the column, in the cave column. So a couple of examples here, both in Catalan. So we have the blast preconditioning on the upper right, and then we have, this is the Cave Urie's PC1 design. So each one of these green ellipses is a man-made fracture that they planned to install in the cave column. The idea is essentially you're reducing the rock mass classification, making the cave more ready to propagate through the rock mass. The next control, although I'm labelling it a strategic control, it crosses the boundary. You design during the strategic phase, but you use the data during the tactical phase of the operation. So it's essentially just a feedback loop. Your draw, which is using your boggers on working levels, is the input, and the output is the cave growth. How do you measure cave growth? Well, that's done through numerous platforms, some high-tech, some very, very low-tech. And they all work very well, but you need to have multiple platforms to manage that information, to provide that feedback. So there's the likes of wireline cameras. These are just cameras on very long steel cables. Allows you to measure the air gap in the top of your cave, and you want to understand if that's growing or shrinking at all. There's the likes of TDR, or time delay reflectometry, which is all telecommunications technology. And then we have some of the more modern sort of instrumentations which are developed by the likes of Alexa Mining, which these are radio frequency identification devices which are able to penetrate through the rock mass at a certain distance. We're also using electromagnetic radiation, which is very similar to a disk drive. When a magnet spins up, it lets out an electromagnetic signal, and you're able to detect that using magnetometers which are spaced around the mine. All of these platforms together give you a picture of what is happening both at the cave boundary as the cave is growing, but also within the cave with your broken rock stack. From that point, you're then able to adjust your draw strategy, how you're actually implementing your cave growth. So for the first few slides, I've spoken about how we manage unbroken material, so the caving, the cave propagation. So what happens when the actual material is broken, it's fractured? How do we recover those resources correctly? Because it seems like a straightforward process, a bit like a chicken feeder. The chicken feeds at the bottom and it all falls out. Unfortunately not. There's quite a lot of complexities around cave flow, and it's still not really fully understood because it's very, like I said, it's a complex system with different material sizes, different material shapes. So we've had a presentation about the ore passes. It's very difficult to actually model these things. So at the moment there's two competing theories. One is the disturbed draw zone theory, or void diffusion model, which I've got highlighted here on the left hand side, and the other is the isolated draw zone, also known as interactive draw. And they both have foundations in physical models, and some have foundations in actual monitoring within active caves. Only the interactive draw theory actually has a design application, though at the moment the disturbed draw theory is more applicable to operations which already have active mines, where they can use that gather data on disturbed draw theory to then implement in future mines. So if you're looking at a brand new mine, a brand new cave operation, you'd be looking at using interactive draw theory to design your footprint. The footprint is where all of the workings happen, where you draw the material out of the cave. It's essentially the rock factory component. The reason it's important is because there's facilities called draw points. The draw points are where you draw the material out of the cave. These draw points have to be spaced closely enough so you can actually draw all of the material out of the cave, because the material flows in an ellipsoid shape, just highlighted here, called the draw zone. And the idea is that your draw zones are close enough together that you have interactive draw, therefore you're not leaving material behind. If your draw zones are too far apart, you're leaving stagnant material, you're leaving resources and reserves behind. However, and there's always a however, if your draw points are too close, the stability of your footprint becomes a problem as well, especially if you're dealing with weak rock masses, because your pillars between your drawbells are very small. So it's always a balancing act. There's also a financial perspective, because drawbells cost a lot of money to create. So it's getting the balance between close enough and far enough apart for stability. Is a particle size distribution. Essentially, this is a forecast of the rock fragments that you would see coming from a draw point. It's based on roughly 200 variables which you gain from your ore body knowledge, and it's based around the rock mechanics, the rock strength, the joint, and the stresses applied. So you essentially plug in all these numbers into a software called BCF, and it provides you with a fragmentation curve. And you constantly update these forecasts as you gain more and more knowledge. So Laubscher in his work looking at physical models and looking at how caves perform, in essence he said, fine materials have a narrow draw zone, therefore your drawbells must be close enough together to get interactive draw. For coarser materials, the draw zone is wider. So we can see here on the right hand side, this is for a finer grade material, the draw zone is narrow, you're looking at roughly 6 to 7 metres wide. And then if you've got a coarser fragmentation, you're obviously looking at 12, 15 metres wide sort of draw zones. Therefore your drawbells can be much further apart and they will still interact with each other, and you will recover all of that ore. So essentially that's the process. So where does Carrapateena sit? Just a plot on the right hand side of numerous other caving operations around the world. At the moment, our PFS study and the work we've done so far suggests that from a drawbell spacing, we roughly sit within the sort of 22 by 32 metre square spacing. You can see some of the other operations in the world, like sort of Cadia, the El Teniente mines from Codelco, who've got lots of experience there. They're in the sort of same ballpark. Essentially, that's the control. That's how we make sure we recover all the resource. We ensure that we don't leave material behind in the cave, and we ensure that our actual working levels is as stable as possible. Just grab a drink. So just moving on now to one of the next hazard. This is mine-induced seismicity. So mine-induced seismicity is synonymous with mining. As we redistribute stresses underground, as we create void spaces, you will see seismicity. It's what happens in mining, especially deep high-stress mining. The stresses that we induce overcome the rock mass strength or the strength of a pre-existing structure. The result is inelastic strain deformation, and we hear or we feel the vibrations, which we refer to as a seismic event. Where these seismic events are close enough or large enough to an excavation, and they can result in the ejection of material into that void space, whether it's a tunnel or a stope or a cave, that's when we're referred to as a rock burst. So yes, the definition of rock burst is the ejection of material into an excavation. And those ejections can be anything from simple bulking, which is where your mesh, your support is bulked out, it no longer looks the same shape. It could be ejection, it's overcome the capacity of the ground support and now you have material laying on the floor. Or it could be the shakedown of a pre-existing wedge structure, so a large volume of rock which is stable under static conditions. When it's shaken violently under dynamic seismic conditions, can overcome due to G-forces the ground support capacity and therefore fall from the banks. So you can imagine the consequences can be quite significant of it. They can range from minor, localised damage all the way to significant production loss, like we saw at Cadia, where for several months they had to go for a remediation and rehabilitation campaign as they replaced ground support which was damaged as a result of their large seismic event. Obviously there's also a significant risk to personnel because we work in these excavations. So in terms of strategic controls to manage seismicity, first one really off the rank is Orebody knowledge. Seismicity is stress, strain and structure, so we need to understand the stresses. We're going to take deep measurements using CSI or HI cells. They measure the in-situ stress conditions. We look at the structure, so we employ structural geologists to understand the structural setting, because many large seismic events is generated around pre-existing structure. And we understand the block mass strengths as well, so we understand when the stresses can overcome the strength of the rock mass. That sort of information, although it doesn't stop seismicity, it helps us understand the likelihood or probability of its occurrence and where it's likely to occur. More recently, the application of preconditioning has been used as a strategic control. So it was recognised that some of the Codelco mines that where they had conditioned their rock mass using hydraulic fracturing, like we spoke about for cave propagation, the actual seismic hazard is reduced. So the images on the right are just two charts which were produced by Eduardo Rojas from Codelco, essentially highlighting the two different mines. One had been preconditioned with the hydrofracking program, and the other one hadn't. So the x-axis is time, so it's showing the time during the cave propagation phase, which is the highest risk phase, which is when you're redistributing lots and lots of stress. And the y-axis is vertical height for the cave column. And the three black lines are essentially the relative level where you have your workforce, your undercut level, your extraction level. So this is where you've got a lot of personal exposure. So the untreated area, we can see a number of these little dots. Essentially, the hotter the colour is, the larger the magnitude event. So we can see quite clearly there's a lot of high magnitude events, not only across the entire cave column, but also around the working levels. So significant risks to workforce. In the conditioned ground, the magnitude event is much lower. There's still quite a lot of events, but because we must remember that seismicity is an exponential scale, an increase in 1 is 10 times in terms of energy. The seismic hazard is much more reduced in the conditioned ground. So this is an application now that many caving operations are actually using, is to precondition using the hydrofracking program of their critical infrastructure areas to reduce that seismic hazard. Another control is around ground support. So ground support is the bolts, the mesh, the concrete that we spray onto the walls. We refer to it as a deformation ground support or dynamic ground support. The analogy would be your crumple zone on your car. It absorbs the energy. It still looks ugly, but it allows you to escape. It allows you to walk out of that area, same as what your car crumples under. The final one is not so much a control, it's helping the control process in terms of forecasting. So again, we can use the numerical modelling, whether it's linear or non-linear numerical modelling, to forecast where we're likely to see high stresses, where seismicity is likely to occur, and therefore apply some of these other engineering controls, such as preconditioning or ground support, or even your tactical controls, which would be removing people from the areas, exclusions and so on. So finally, I'm just going to speak a little bit about mud rush, which is the final hazard I wanted to speak about. Not a lot of information, so don't stress. So essentially, mud rush is the inundation of mud forming minerals into the working. So mud happens, or the mud rush happens when you get sufficient water content and mud forming material. So mud forming material would be anything below 5 millimetres in size. So the image on the right is taken from Freeport's deep ozone mine. Freeport owned in the West Papua, where you'd expect to see meters and meters of rainfall. You obviously have mud-forming minerals, and this is a consequence. Whoops, sorry. So we can see here this material is running out. This is one of the draw points. Possibly not the clearest, but the material is pushed out across the drive, and you can just see it just above his ankles. This is quite a low level sort of mud rush event for Freeport. They have significant controls in place for the areas which are susceptible to this. There's no entry for personnel. Essentially, this is a very old image. It's all tele-remote loading and so on. So in terms of consequence, significant risk to people underground. It could be a short term, the time it takes to clear up the material inundation. It could be sterilisation as you walk away from a particular area which is susceptible to mud rush, or it could actually be the closure of the operation. So in terms of strategic controls to manage it, again it falls back to Orebody knowledge. There's two areas you need to understand. Firstly, which of your lithological sequences can form mud-forming minerals. The other is looking at your regional and mine scale hydrological model. Others are around mine design, so ensuring that your surface infrastructure drains water away. If you have a 1 in 1,000 year rain event, you don't want that water entering into the mine working, so we need to have bunding and drainage systems to ensure that doesn't happen. Some of the underground workings also, they penetrate into the cave, so we need to ensure that they're graded, so any water, any spillages from surface water actually drains away from the cave, so avoiding any material, any water inundation into the cave itself. Similar to the seismic risk, we also use numerical flow models to help us forecast the event or the time when these events could actually occur if we felt that they were important. On the right-hand side is a very simple but a very beautiful piece of work from my colleague Dr. Hocking, who's unfortunately not here today, but essentially he used a cement mixer to determine which of the ore units or which of the lithological units is most susceptible to breaking down to be a mud-forming mineral size. So essentially putting sections of drill core or different lithologies into a concrete mixer and leaving them in there for some time, and then putting them through a set of sieves. So yes, you can see it's generally the host material, and then we have one of the overlying sequences. One of the sandstone units breaks down quite readily, so if there's a mud-forming risk, that would be the unit. So that brings me to the end of my presentation. So I just say thank you very much to IMM for giving me the opportunity to present, and to Oz Minerals for giving me the permissions, and for everyone for listening as well. So that's the end. Thank you very much.